number 4. Am I good to go on? So that was number 7. On what, 5.3? A little belated. All right, so here we go. Number 4 on 5.3. All right, so this problem really, the first part of it is just kind of an exercise in understanding how to solve these Pulley problems, okay? And then the second part of it is some calculus, okay? And I know for a lot of you the calculus is new. I'm going to try to keep leaving the calc off the test until you guys had a little bit more exposure to it. That being said, I do think that this, has everybody learned the quotient rule?
Yeah.
Is there anybody who's not? Okay, no. Okay, so theoretically this is a thing you should be able to do, but I'm going to, give you guys time to master that a little better. Okay, so here we go. So we've got a pulley system. This block over here has a mass of, where did it go? 2.8 kilograms. All right. This block over here has a mass of only 1.3 kilograms at the start of the problem. So first of all, which way is the system going to go? Down. Yeah, down. It's going to go to the right, yes? So I'm going to call it to the right positive. Good? All right. Now, what makes this problem challenging is that the mass of block 1 is changing, right? Because water is falling out of it. Okay? So,
I think it's block 2.
Block 1.
Oh.
yeah, it says at time t equals 0, it has a mass of 1.3, but container 1 is losing mass through a leak at a constant rate of 0.2 kilograms per second. So, the mass of 1 at time t is actually 1.3 minus 0.2 t kilograms, right? Does that make sense? I heard a lot of yups. Is anybody confused about how I got that? Yeah.
What was in the parentheses after M?
That? Oh, t, as a function of time.
Okay.
Right? Because the mass changes as time goes on. Cool?
Yeah.
Everybody good? All right. So, come on, computer. There we go. All right, so let's think about our forces. So over here, we're going to have gravity pulling down, right? So that's going to give us a force of 2.8 times g, right? And over here, my force is going to be changing. So it's going to be 1.3 minus 0.2 t times g, right? Follow or no? All right. I should make one of those negative. Which one? This one, right? So if I make it negative, I can just rewrite this as 0.2 t minus 1.3 g. Yes? To make it negative? Are we good or not? Bless you. Ann, you good back there? Everybody good? Okay, so the net force on our system as a function of time is going to be 2.8, is going to be 2.8 g minus this mess, 0.2 t minus 1.3 times g. Follow? So if you simplify this mess, it gives you 4.1 minus 0.2 t all times g. So there's our net force as a function of time. I will highlight it so that it stands out. All right, so a little bit of algebra there, but are we all cool with that? Let me make sure that jives with the work that I've got written down on this piece of paper. Wait a minute. Oh, I subtracted a negative. Dang it. Sorry, I knew that looked funny. I made this negative to indicate that it was going in a negative direction.
Oh.
So I should have added that negative force.
Oh, yeah.
So this should be plus. Shoot, let me rewind. I'm sorry. Didn't know you could erase the highlighter. I knew that looked funny. So it ends up giving you 2.8 minus 1.3 is 1.5 plus 0.2t times g. There we go. Sorry about that. I will re-highlight that in a new color. Okay, everybody cool with how I got that? I apologize about the little mix-up. Any problems? Yeah, I know, because of physics. All right, everybody good? Any questions? All right, now we can also write a function for the mass of the system. So this is the system, right? We can also find the mass of the system as a function of time. Well, that's going to be our starting mass, which is 4.1 minus what's leaking out, right? So 4.1 minus 0.2t. Follow? Do you guys agree that that is the system, the mass of the system that's accelerating at any given time? Cool? So, yes, we're going to get to that in just a second. Okay, so that means that the acceleration of our system at any given time is net force over mass. So that's 1.5 plus 0.2t times g all over 4.1 minus 0.2t. Good? All right, so now we got to take, so that's the acceleration at a given time, right? And the problem wants to know at what rate the acceleration is changing. So how do you find the rate at which something changes, you guys? Take a derivative, right? So that's going to be my next step. So the question wants to know what that is. Cool? All right, so I did something that might not have occurred to a lot of you. I didn't want to deal with these 0.2s. So I multiplied the top and the bottom of the fraction by 5. Does that make sense? Because that'll just give me 1. Is that going to mess? I mean, you could do the next step without doing that, but I think it makes the next step easier. Is that okay if I go ahead with that route? Okay, so if you multiply by 5 on the top, you get 7.5 plus t over, on the bottom, you get 20.5 minus t, and then that's all times g. Oh, shoot. Ah! Why are you going to be that way? Cool? All right, so now I take the derivative of that, right? So let's see, the derivative of a with respect to t is like high d, low d, high d, something, I can never remember it. So it's derivative of the top times the bottom, is that right? Minus?
Yes.
Is that right? Okay, so the derivative of the top is going to be 1 times the bottom minus the derivative of the bottom times the top. All over the bottom squared.
Multiplying it by 5 is a lot easier.
Doesn't it? Good?
7.5 plus t.
So we can simplify that.
Yeah, plus was-
Oh, I did forget the plus, sorry. Yeah, that would have been bad. All right, so let's see. We're going to get 20.5 plus 7.5, so you get 28. Minus t. It's supposed to be minus 2t, I thought. What did I do wrong? Am I dumb? What did I do? Oh, right. Oh, yeah, the t's cancel.
Yeah.
Sorry. Over 20.5 minus t squared. Oh, I forgot the g. My bad. Ah! Geez, I am doing a rotten job of keeping track of stuff. Okay, everybody good up to there? All right. So then to solve a, it says at time 0, at what rate is it changing? So you just plug in 0 for t. To do b, just plug in 3 for t. Good?
Yeah.
All right. And then finally, let me see, are we gonna, if we keep going, are we gonna have time to finish the lab tomorrow? I think we'll be okay. I think we'll be okay. I'll give you guys plenty of time to do the lab. So, or to do the, yes. Okay. All right. So everybody good up to here?
Yeah.
Okay. So finally, part C is kind of weird. It's sort of a dumb question, but I like it because it really forces you to think. It says, at what time does the acceleration hit its maximum? Okay. Well, the problem is, as the time goes up, your acceleration goes up, right? Always. So according to this equation, the bigger your time gets, the larger your acceleration gets, basically, right? There's a little oversimplification there, which conceptually makes sense, right? Because as this side gets lighter and lighter, isn't the system going to move faster and faster?
Yes.
Okay? But there's still a max. At what point do we achieve maximum acceleration?
6.5 seconds.
Why 6.5 seconds?
That's when you're out of water.
Yeah, once this mass gets to 0, that's as fast as it can go, right? So when does that mass get to 0? Well, you've got 1.3 kilograms, and you're losing 0.2 kilograms per second for some number of seconds, and you want it to be 0. So in other words, how long does it take for your mass to go down by 1.3, right? So it takes 6.5 seconds. Cool? All right, questions?